Hello everyone and welcome to another video on solving a LeetCode problem with APL. Today we will be solving problem 79 as per a request by one of you. So someone opened an issue on the GitHub repository where I host all of these solutions, and they asked me to solve problem 79, so we will be taking a look at that. And problem 79 is it's simple to understand. So the problem statement says that we are given a board of letters, like this one over here, and we are given a word. So in this particular example, the word is C. And then we have to look for the word in the board. And in this case, the word C is over here. It starts with an S, and then the E, and then the E. And the restrictions are those that you could probably guess. You're not allowed to repeat letters, and the word must be you must build the word from adjacent cells, from adjacent letters. So, for example, there's another word here, and that's A, B, C, C, E, D, and you build it with A, and then the adjacent B, the adjacent C, the adjacent C, the adjacent E, and then the adjacent D. That's how the problem works. And in this video, we're going to have two parts to it. It's going to be slightly longer than usual because this is a medium problem, and I want to explain the solution fairly well. So I'll start with a recursive solution and then an array-oriented solution. Both are similar in the way they solve the problem. It's just the way that the code is written that changes. And the first one is going to be the recursive one because it's the approach that's more similar to how you would probably solve this in a more traditional programming language. So if you have experience in other traditional programming languages, you can start with this one and then check out the array-oriented solution, or you can just simply skip to the array-oriented solution if you don't care about the recursive one, because the recursive one is not the most elegant way to do it in APL. And so how will the solution work? It's going to be like this. So we have a board, and in this case, in this particular example, there's 3 rows and 4 columns. And the idea is that the solution works as follows. It receives a board like this over here, and a word that has a couple of letters. So what it does is it looks for this word, it looks for the first letter in the board. For example, there's an A here and an A here. So it's going to look for the letters, and it finds one over here and one over here, and then it recursively attempts to use each one of these letters. So what it's going to do is it's going to try to use this cell right here. So it scratches this off. It's done with the first letter, and then tries to find the second letter. So for example, if the second letter is a C, it's going to try and find it. Let's see if I can change colors. So let's pretend there's a C here. So it checks off the first letter and tries to use this A, and then it looks for the C, but finds that this C is too far away from that A, so this is not a valid way to build. And so it goes up the recursion, and instead of using this A, it uses this one, it scratches it off. And then it checks, okay, there's a C here, okay, we can use this C, this is close enough to the A that we previously used, and then it keeps on going. So that's the idea. How can we do this? Well, let's define the board, which is the 3-4 shape of the letters we had. So that's the 3-4 shape of A, B, C, E, S, F, C, S, A, D, E, E. And then the word, let's start with C. Or actually, you can start with A, B, C, C, D, E, because this is longer and we want to make sure that our solution works with longer words. So now let's edit the, was it find word? Sorry. No, word search. Let's define the word search recursive function. So how does that start? Well, first we split the right argument into the board and the word we are looking for. And we do that because we want to use the left argument for the recursive information regarding the positions that we already used. So that's going to be on alpha. So omega splits into the board and into the word. And if the word is empty, then it's because we found the word in a board. So we can quit with a 1. Otherwise, we need to do something. Now, what do we do? what we need to do is we need to take a look at alpha. The alpha comes into play later. What you need to do is we need to take a look at the first letter of the word and find it in the word. So the first of the word, and then we look for it in the word, and then we use where to figure out the positions where the next letter is. So it's a where. Okay? And now what we should do next is check if these positions are close enough to the last position used, which is going to be on alpha. So alpha stores the position from where the last letter came. So there's a C here, and when we try to figure out what the C is, we need to know that we use this A over here. So that's what's going to be on alpha, right? But alpha, and then what we can do is we can check the distance between these two. We can check the distance in a two-dimensional plane, and it's going to be horizontally there's no distance between them, and vertically there's a distance of 1. And so summed up, this gives a total distance of 1, right? And for example, this right here, these two cells, they have a horizontal distance of 1 and a vertical distance of 1, and all summed up it gives a distance of 2. This is called the Manhattan distance. So we compute the distances and we only keep cells that are the correct letter and close enough, right? And alpha, in the beginning, we have no information about it the very first time we call the function. And so we need to put something in alpha that is good enough that will allow all of these initial positions to be used successfully. And so actually, I don't know why this is over here. We need to put it down here. So what we're going to do is we are kind of cheating in this particular line of code. We are kind of cheating. So what we do is we take the position, and to it we add 1 0. Okay. So this is cheating in the very first call. Let's remove in the first call, because now if you kind of ignore this line of code, what do we have? We have the positions of the next letter, and we have alpha that tells me the previous letter used. So what we can do now is we can check the positions and subtract alpha from them, because now we are going to get the differences, the distances between the two of them. So if alpha is, let's pretend that alpha is this position right here. So that's going to be 0, 1, 2, and 0, 1, 2, 3. So this is position 2, 2. So alpha is 2, 2. And now we are checking the C over here, which is position 1, 2. So 1, 2. So this is a vector of positions. Now what we can do is we can do the position minus alpha. Now we're going to have a list of offsets like these that I showed. We're going to have a list of offsets, and then we can figure out which we put this in absolute value, because the distance between this cell and this one is the same as this cell and this one, but the offsets have different signs. And then we can just sum things and find out where the distance is 1. So we do the absolute value in here. Now what we can do is we can mix this and sum over the columns and find where the distance is 1. So these are the legal positions. Are they? These are the legal. So this is a Boolean mask pointing at the legal positions, so the positions that are close enough, and then we can actually compress right away to only keep the legal positions. And then what we do, we just call the function recursively, because this finds out what the next step can be depending on the word, on the letter that we just looked at. And now we just need to keep going down recursively, figuring out all the possibilities. So how do we do that? We are going to have a little diffn over here that's going to go over the legal positions. Now for each possible position, we need to call the function, we need to call this function again on a word and on a word. Now the word is the same word we have, except we can drop the first character, and the board should be this word that we are using, except we need to remove the letter we just used in some way. And how can we do that? Well, we can, for example, replace it with a character that never shows up on the word. For example, quad UCS 0, because this is the null character. So we can just take the board and we can take the null character and use the @ operator to put it in a position, for example, in the upper left corner. And this makes sure that this is no longer used in the recursive calls. So we can do that. We can take quad UCS 0 and put it at the position we are currently using. And that position is given by omega because it comes from the legal positions. And we do that on the board. And then finally, we need to, let's make this longer. We need to pass in the updated information about the letter that we just used. And we do that with the left argument of the word search. I don't know why this is rev, it should be rec for recursive. And so we do this. This is the recursive call. And then we just need to gather the results and look for any match. So we do an OR reduction. So now we fix the function and we can try calling it with the board and the word. Oh, and it fails because I did something wrong. So let's see if I just type the things. Oh, I didn't type things correctly. So the word I typed was ABCC, so that's A, B, C, and then C, and it should be ED. It should be ED, and I typed DE. So let's update the word, ABCC, ED, and look for it again. Okay, now it worked. Now let's change the word to C, which should also work. And then the problem statement includes another false case, which is ABCB. So let's try ABCB. All right, so this is a recursive approach. And I'll be completely honest with you, given my experience with other programming languages that I learned before learning APL, this is the type of approach that comes to my mind first. It's this kind of recursive approach. But this is not the best APL solution. And it's not the best APL solution because I have another solution to share with you, which is more array-oriented. And that one is also probably not the best array-oriented solution, but it's better than this recursive solution. So let's take a look at it. Let's work with our board and with our word. But actually, it's simpler to show you how it works if I start with a smaller word. Now the idea is still the same. We're going to take the board. Sorry, it's actually helpful if we start with the word. We're going to take the word and compare it to the board with an outer product. And what this does is it creates slices, or it creates planes where each letter of the word is compared to the board. So now I know that if I am to find a match, then the first letter of the match comes from one of these two positions, and the second letter of the match should come from one of these positions, and the third letter of the match should come from one of these three positions. So now we do this to get all of the possible matches. And by the way, essentially what we are going to do is build all of the possible paths through this board with the letters that make sense, and then we just need to check if they don't reuse letters. So that's our game plan. Now what we're going to do is we're going to use the where primitive on each plane separately. And so we use the rank operator to tell it to operate only on matrices, because matrices have rank too. And so what this does is it applies where on each plane. But it gives the result like this because of the way that the rank operator has to preserve the shape of stuff. So what we can do is, and I know that shape of stuff isn't a very technical term, but what we're going to do is we're going to enclose it like this so that we get the results in this form. Alright, so now we have a vector, and each position contains all of the indices that could be used for that given position of the match. So, and that is to say, if the word is in the board, then the S must come from one of these two then the S must come from one of these two places, the E should come from one of these three places, and same thing for the next E. Now what we're going to do is we're going to take this and we are going to build all the possible paths. And we do that again with an outer product. And now the outer product with catenate will combine all of the things, except that we need to insert the outer product in the middle of these smaller vectors. And so we use a reduction for that. And so this reduction will insert the outer products in the middle of these smaller vectors in here. Except when we press enter, we get things like this. And what's the issue here? The issue here is that the outer product with catenate, actually I think it's easier to show you. So let's take this vector and this vector here. So it's the 1, 0, what was it? 0, no, 1, 3, and then outer product catenate with 0, 3, 2, 2, 2, 3. So 0, 3, 2, 2, 2, 3. So the thing is, these are just simple vectors, and so when they get catenated, they produce a larger vector. Whereas what we actually want, is for these indices, two-dimensional indices, to remain inside their scalars. So we can actually do the outer product, and we catenate over the enclose. And so we make sure that we catenate the scalars. So okay, we can try this out. So let's build all of the paths again. Except now things are getting too nested. Alright, because at some point we already have things like this and we don't need to enclose them again. Notice that there's an extra box in here. So what we actually want to do is, instead of a plain enclose, we want to enclose if simple. Alright? Right. And then what? So now we have built all of the paths, all of the possible paths. Sorry, let me think for a second here. Let me see what happens if I put a longer word in here. So the A, B, C, C, E, D word. Yeah, I think the depth increased. Let me check. Yeah, now instead of using this one, let me just use my word. No, the depth didn't increase. This looks different. Let me make the font size just a little bit smaller. So let me make it larger again. Now let me go to the end of the session. So with the word, I have something like this. So if I mix twice, so I need to mix thrice, and then what's the shape of this? And then if I use the long word, right. Okay, so I'm just checking how the length of the word influences the dimensions of the things we are building. And why is that? Because as we keep doing the outer products, I think, is it the outer products? I don't want to be, because I know how to fix this because I played around a lot with this, but I wanted to recreate the reasoning that leads us to having to do what I'm about to do. Right, so the first thing we need to do is this close. Yeah, so we disclose because there was a reduction on this vector, and I don't want the final, I don't want an actual final scalar, because a reduction always reduces the rank. So this was a vector, and in the end I don't want the scalar, I want what's inside. Whoops, I forgot to do that. I want what's inside. So, gosh, how did I delete that? Okay. I want what's inside. But then the thing is, the rank of what's inside increases with the length of the word. Because of the successive, right, because of the successive outer products. Obviously, that's it. But I don't want the rank to keep increasing. I want to keep things always at the same level, regardless of the length of the word. Because outer products, that's what outer products do. They increase the rank of the things you are working with. So a vector outer product with a vector generally builds a matrix. Okay? But I want to keep this small. So what we can do is, let's maybe do it with a different, I don't know. As we keep, no, I don't want, sorry, I don't like the different here. So as we keep doing the outer product to combine all the possibilities of index choices, we want to flatten things. We want to merge the two leading dimensions because we have a series of choices that we're going to combine with the indices for the next letter, but we don't want to create a higher rank array with the major cells containing or representing each possibility or each choice for that particular letter. We want to keep everything flat. And so as we do the reduction, we also used catenate with the first two axes to melt the first two axes into a single one. And so when we do this, we see that this has a more flat structure. And the structure will look the same for words of different length. And now if we mix twice, we always get something of rank 3. Each slice represents a possible path, each of the 3 rows represents one possible letter, and each of the 2 columns represents one of the indices. So this is the first index and the second index. So this was what I was trying to think about. So this is melting the first 2 dimensions. And let me show you just very quickly. Let's see, we can take a look at this again, and then the board. So this is a 3-dimensional array, and if we melt the first 2 dimensions, then we are essentially getting rid of these spaces. So this is the first plane, the second plane, and the third plane. This operation right here probably has a name, but I can't remember it, so I'm just calling it the melting of the first 2 dimensions. We are fusing them together. Alright, now we have this. We have a 3D array that contains all possible paths. Now we just need to do 2 things. We need to first check which paths only use consecutive letters or adjacent letters. And we also need to check which ones don't reuse letters. For example, this path uses the same letter twice. Or this path right here has a big jump from this position to this position. Sorry, from the first to the second. So we need to get rid of those. So how do we do that? Well, these are the paths, so we can save them. Now what we can do is we can do a pairwise reduction along the axis number 1 to figure out the difference between this one and this one, and this one and this one. So we are going to check the distances. So this is the distance for these are the 2 distances for the third path, sorry, for the last path. These are the 2 distances for the second to last path, etc. And so we need to do something similar to what we did with, what was it called? Word search rec. Where is it? Yeah, it's something like this. So now we are checking the distances. So now we need to do the absolute value, we need to sum things, and we need to find the ones where the distance is just 1. So we do, what was it? So these are the differences, we do the absolute value. And now each column represents a distance for one coordinate, so we need to sum them up. So we can do a summation on the last axis, which would actually be with a reduction over the last axis. Now we need to check which ones are equal to 1. And then we need to check where all of them are consecutive ones. So what's this? So this is the two distances for the first word, the two distances for the second word, all the way to the two distances for the last word. And this shows that the first letter to the second letter only had a distance of 1, so this is nice. But then from the second letter to the third there was a jump. Whereas in this one we can see that from the first letter to the second letter there was only a jump of 1, and from the second letter to the third letter as well. So this is what the and reduction here is checking. It's checking which ones only use adjacent letters. And we can already see it's only 1, but in general we might get more of these. So after doing this, these only use the adjacent ones. So we can compress the paths, and after we have all the adjacent ones, notice this is a rank 3 array, we need to check which ones only use unique unique cells. So how can we do that? We can take a look, for example, at paths, because there's more possibilities here. And now what we can do is check if all of the rows, all of the unique rows match the slice itself, and we can do this for each of the slices. So this is unique, and unique when applied to a matrix. Let's see, paths, can I get the first slice? So if I apply unique to this, it's going to drop the repeated rows. So this checks if after dropping the repeated rows I get the same thing as what I had, and I do this for each slice with rank 2. So this gives me another mask, and in the end I only need to check if there's something unique in here. So we started out by computing the paths, then we figure out which ones are the adjacent ones that only use adjacent things, and then we check which ones only use unique cells. And we need to check if there's any one that is valid. And this is what we should return from our function. So let's edit the word search from, let's just call it this, because this is what I would say is the best solution of the two I showed. And we just need to copy this from here to here. I don't know why I didn't copy all the lines at the same time. Alright, and then we need an OR reduction here. So let's see. Wait, actually, sorry, my bad. Instead of word and board, let's keep the signature the same. So let's do the board and the word coming from Omega. Okay, so word search, the board and my word. What was the word? It's the C word. So now let's do the longer one, and then let's do something that doesn't exist. Okay, so it appears to be working. So yeah, these are two possible solutions for this problem. I would be more than happy to see your alternative solutions and suggestions. And just bear in mind that when you drop some comments below with APL glyphs, things get all mixed up, or more often than not, YouTube automatically deletes the comments. So make sure to maybe just raise an issue or a pull request on the GitHub repository with your alternative solution instead of typing it in the chat, because it's probably going to get deleted and I won't be able to see it, nor will anyone else. Alright, so I think this was it for now. I realized this was a longer video than usual, so if you reached this point, let me know if this was just too much or if it was bearable. And if you have any questions, feel also free to, well, ask them. And yeah, I'll see you for the next one. Bye.